Hello students, I'll be briefly going through worksheet 1 for reaction kinetics. Again, I know that I've gone through the guided inquiry in class, but some of you weren't around, so I thought recording this will help. And of course, those of you who are around, you can review some of the things that you weren't very familiar with. Okay, so this worksheet began by giving you a definition on what exactly we meant by a rate for reactions. Okay, so I think over here you can see that the rate of a chemical reaction, you can determine it from either the perspective of the reactants, how quickly they are being consumed, or how quickly the products are being formed. Right, so over here they mentioned that by convention, rates of reaction, consumption, production are always reported as positive numbers. Okay, so this is important. They are reported as positive numbers. So from what we mentioned earlier on, if you look at the change in the molarity of a reactants, over here we are really looking at how the concentration of the reactants or the products change with respect to time. Of course, because they are always reported as positive numbers, you need to put a negative sign over here. Why is that the reason? Because you will know that for reactants, say initially you have X amount at T equals 0. Okay. After some time, let's say at T equals to T prime, the new X prime will be less than X. Okay. So the change in the concentration will inevitably be a negative number. Yeah. So therefore, you need the negative sign to actually negate the calculation so that you will end up with a positive number. I think this is being asked in question 2. So what is the purpose of the negative sign in equation 1? Right, so for the change in products over time, you do not need a negative sign to negate anything. So I'll just erase this so to make it clearer. Okay, so rates of reaction equals to minus D concentration reactant dt or plus D concentration products dt. Right, so let's go through question 1. If time is measured in seconds, what's the rates for what's the unit for the rates of reaction? Okay, because we are looking at change in the concentration, so we're looking at moles per dm cube. Okay, and then we divide this by time, and time is measured in seconds, so this will be per second. Okay, so this will be the units for the rates of reactions. Right, so d reactor dt will be a negative number. I think we agreed earlier on, because I think I highlighted to you that at time t prime, x prime will be a smaller number than x. Yeah, so change is defined as final minus initial, so that will give you a negative number. Okay, so that will be a negative value for reaction 1. Okay, then the purpose of the negative sign is really to negate the negative sign to make it a positive number. Next, we'll look at this particular reaction. Okay, so this reaction described in equation 2 was carried out times equal solution with a volume of 2 dm cubed. I think this is a very important clue here. The volume is 2 dm cubed. Some of you might not notice it. Okay, and table 1 displays some data related to the experiments. Okay, so this is 2 dm cubed again, so they emphasize it. So so this is an increase in time from 0 to 100 seconds. You notice that the amounts, so this is number of moles, this is in amounts, not concentration. It dropped from 2.40 to 1.80. So there's a change of 0.60. Okay, so what's most important here will be we need to look at the stoichiometric ratio of chlorate 1 to chlorate 5. So the ratio in this case is 3:2:1. Okay, so this is important. Yeah, because of this stoichiometric ratio, the drop in the amount of chlorate 1 by 0.06 will means that correspondingly, right, the chloride will increase by the corresponding stoichiometric ratio. So you need to multiply it by the appropriate ratio. Okay, so in this case, we're going to multiply 0.6 by 2/3. Yeah, so I'm going to expect this to increase to 0.40. Okay, and then for chlorate 5, 0.20. Okay, so this still keep the ratio to be 3 to 1. Yeah, so this is very important, so just take note of it. Right. Okay, so fill in the entries, we have done that. Based on the data in table 1, calculate the following. The rates of consumption of chlorate 1. Okay, so right now we know that the decrease is 0.60, right? So in this case, the rate of consumption of chlorate 1 will be, this is equals to minus, okay, so bracket 1.80 minus 2.40, okay, over dt, okay, so this is over dt will be 100 seconds, okay, but we need to remember this is the change in amount, okay, but remember, rate of reaction is measured usually in terms of the change in the concentration, right? So we need to divide, so this is concentration, we need to divide this by 2, so divide by 2, okay, so we punch calculators, okay, quickly, we should get 3.00 times 10 to the power of minus 3 moles per dm cubed per second. Alright, okay, so we'll do the same. We'll do the same for the production of chlorides and chlorate 5. Okay, so we'll do the same. So this will be 0.40 minus 0.0. Okay, divide by 2 over 100. Okay, so this will be 2.00 times 10 to the power minus 3 moles per dm cube per second. Okay, we'll do the same for this. So this will be 0.20 minus 0.0. Okay, divide by 2. 100 equals to 1.00 times 10 to the power minus 3 moles per dm cube per second. Right. Okay. Okay, we're going to move on to the next part. You were told that to simplify things, the rates of a reaction can be defined as the rates of consumption of a reactant or production of product whose stoichiometric coefficient is 1. Okay, this is usually the case, but not always the case. So I think this is written as a general statement, so we have to be very careful about it. Again, always go back to the chemical equation that you are dealing with. Yeah, so again, this is quite generic, so do not just follow it blindly. Okay, right, so the rates of reaction can be expressed in terms of the rate of change of any of the reactants. So this is in general as well. Okay, so based off your answer to question 4, what is the rates of reaction of 2 as written in equation 2? Okay, so again, as written in equation 2, so equation 2 is over here. Okay, so if you look at this, the rate of reaction, so based on the generic statement given in the box, so we should be looking at probably the rates of production of chlorate 5, right? Okay, so therefore the rates of the reaction, so rates of reaction of 2, okay, so it's equals to 1.00 times 10 to the power minus 3 moles per dm cube per second. Okay, so again, let me emphasize that this is generic, okay, so it doesn't always represent 100%. Okay, so you can actually represent the rates of a chemical reaction using any species as long as you define it clearly. Yeah, but this is just to make things simple, so do not be bound by it too much. Right, okay, so for the data in table 1, you can write the following relationship. Okay, so that's table 1 over here. Okay, so that's table 1. You notice that there are also incident ratio 1 to 2 to 3. Okay, then the rate of reaction is half the rates of production of chloride. Okay, so write a similar equation to describe the relationship between the rate of reaction and the rate of production of chlorate 5 as well as the rate of consumption of chlorate 1. Okay, so in this case, I'll just write it down. Rate of reaction is equals to half rates of production of chlorides. So this is dCl minus dt. Okay, simply by looking at this, Okay, so this is 1 to 2, right? So if I halve this, I will get back 1.00. Okay, and then at the same time, for consumption of chlorate 1 is over here. Yeah, so the ratio is 3 to 2. Sorry, 3 to 1. Yeah, so I'm really looking at minus 1/3 d ClO minus over dt. Okay, so I hope this is clear enough. Okay, then express reaction 2 in terms of the change in concentration for each reactant. Okay, so I think I've illustrated it over here, except that I'm just going to replace this with d ClO3 minus over dt is equals to blah blah equals to blah blah. Okay, so this will be the answer to question 7 over here. Okay, so it's basically just trying to showcase to you how you are going to write the rate of a reaction with respect to the reactant and the product. Yeah, but you multiply it by the correct fraction so as to ensure that you get the same value and you know what you're defining. Yeah, so most importantly, I hope it's not too confusing. You need to know what you're defining, you need to know what you're calculating, and then the rest are just details you manipulate along the way. Okay, yep, then I'm going to move on to this important part. So there are some of these questions, I think they have already been covered in the lecture videos, so I'm not going to go into details, but I'm just going to end off the this particular video by emphasizing what's the difference between average, instantaneous, and initial rates. Okay, so you really need to know the difference, because if not, then you're going to get super confused when you work through kinetics. Okay, so for example, I'm just going to illustrate it using this simple example. Let's say this is the concentration of ClO3 minus. Okay, ClO3 minus is the product over here. Okay, so I'm using a very simplistic discussion here, so do not think that it really varies this way. So I'm just going to showcase it simply to illustrate some points. Okay, so let's say the rates of production of chlorate 5, it goes through a curve like this. Okay, for example. Okay, so right now I'm just going to explain what is the difference between average, instantaneous, and initial rates. Okay, initial rate will be the simplest, so I'm just going to use a line here, a blue line. So it will be if the instantaneous rate at time equals to 0. Okay, it will look something like this. Okay, not the best, but you get the point. Okay, so this is initial rates. Okay, so I'm just going to use blue. Okay, so initial rates. So basically, initial rate is the instantaneous rate at time equals 0. Instantaneous rates you can define as any time you want. So for example, if you feel like it, you can say that, okay, I want the instantaneous rates at time equals to t1. Okay, so this is over here. Okay, so I'm just going to put a dot here. Okay, so I'm just going to use green. Okay, I'm just going to try to draw a straight line. Okay, not the best. Okay, not too good at this. Okay, hope I can shift the curve. I don't know how to shift. Okay, I can't shift. Okay, so because I can't shift, I'm just going to try to draw the line nicely. Okay, so here, just going to put a dot here, and then I'm going to draw the line. Okay, so you get a point. Okay, probably curve a bit more to the right or a bit more to the left, but yeah, so this is the instantaneous rate. Okay, so this is the instantaneous rate at time equals to t1. Okay, right. So then the next question is, what about the initial rates? Sorry, not initial rate. What about the average rates? So what exactly is average rate? Okay, so average rate is really up to you to define. You need to know the time frame you are talking about. So let's say we are looking at the average rate from the time frame 0 to t1. Okay, so in this case, I'm going to illustrate using the rate. Okay, so I'm going to start from here. Do it like that. Okay. Okay, So this red line will be the average rates of the reaction from 0 to T1. Yeah. Usually this is not mentioned, but of course when you are calculating average rate, you have to indicate the range you are dealing with. And then later on in worksheet 2, you're going to deal with clock reaction. You'll notice that the smaller your T1 is, the closer will your average rates be a good proxy to the initial rates. Yeah, so that's something you are going to recognize for the iodine clock reaction in worksheet 2 later. Okay, so with that, we have come to the end for the review of worksheet 1. I think for the remaining questions, you can go through it on your own through the lecture videos for the particular section of the notes. Okay, so of course question 4, sorry, I forgot to answer question 8. So question 8 actually asks, state if the rate found in question 4 are instantaneous, or instantaneous, average, or initial. So of course here we are really looking at an average if you look at this, because we are not determining the amounts of, we're not measuring the amounts of the reactant or the product at every time frame. We are just having 2 time frames, 0 and 100. Yeah, so table 1, so the question, for question 4, we are really looking at the average consumption and the average production of the reactant and product respectively. Alright, so I'll see you in the next video.